Next, calculations involved in redox reactions. See, whenever the first topic is balancing of the redox reaction. First, if we balance the redox reaction through the procedure what we have discussed earlier, we can solve the problem very easily. But the drawback of that procedure is, if you just know the total reactants and products, we can balance the reaction, then we can proceed for numerical calculations. But sometimes if we do not know the actual nature of the products that are being formed, we can't balance the reaction. Therefore, even without the knowing the actual products that are being formed, we can solve the numerical problems related to redox reactions. How to solve the numerical problems related to redox reactions? So, in all the redox reactions, first you identify the what is called valence factor or N factor or change in the oxidation state of every reactant species. For example, let us take the KMnO4. When KMnO4 participates in the reactions, so KMnO4 will always gain the electrons. The actual number of electrons gained by the KMnO4 depends on the medium in which reaction takes place. In acidic medium, it will gain certain number of electrons. In alkaline medium, different number. In the neutral medium, totally different number. Therefore, if we just know the medium in which reaction is taking place, we can identify the number of electrons gained by the one molecule of KMnO4. So, for example, if the reaction takes place in acidic medium, one molecule will always gain 5 electrons, hence it converts into Mn2+. Since one molecule is gaining 5 electrons, hence we can call N factor or valence factor of the KMnO4 in acidic medium is 5. By using this valence factor, we can solve the numerical problems very easily. Similarly, KMnO4. When KMnO4 participates in the reactions in alkaline medium, one molecule will always gain 1 electron. Therefore, this KMnO4, it will be converted into K2MnO4 minus. One molecule will gain 1 electron. Next, KMnO4. When it participates in the reactions in the neutral medium, one molecule will always gain 3 electrons. Therefore, it will be converted into MnO2. So, therefore, just if you know the medium in which reaction is taking place, we can easily identify the number of electrons participating per one molecule. That number of electrons participating per one molecule itself is called valency factor or N factor. By using this N factor, we can calculate the equivalence of the KMnO4 participating. Therefore, valence factor of KMnO4 is equal to number of electrons exchanged by number of molecules participated. Number of molecules participated. Similarly, for K2Cr2O7. K2Cr2O7 also always act as the oxidizing agent, but here the number of electrons gained by the K2Cr2O7 is always fixed. Whether the reaction takes place in acidic medium or alkaline medium or neutral medium, one molecule will always gain the fixed number of 6 electrons. Therefore, here each chromium will become +3. Hence, valency factor of the potassium dichromate is 6. Valency factor. Similarly, oxalate or oxalic acid. When oxalic acid or oxalate participates in any reaction, one molecule will always one molecule will always supply 2 electrons. So this this carbon and this carbon both will be converted to 2 CO2, here 2 electrons. Therefore, since one molecule is supplying 2 electrons, the valency factor of the oxalic acid is 2. Oxalic acid. Similarly, hydrogen peroxide. One molecule, hydrogen peroxide, it can act as the oxidizing agent as well as reducing agent. If it acts as the oxidizing agent and if it acts as the reducing agent, whether it acts as oxidizing agent or reducing agent. Oxidizing agent means electron gainer. So one molecule will gain 2 electrons. Here if it acts as reducing agent, one molecule will supply 2 electrons. Therefore, number of electrons participating per one molecule is fixed, whether it is oxidation or reduction. Oxidation or reduction. Now, Now let us take one example to identify the valency factor and how to proceed for the calculations of numericals involved in these redox reactions. Let us say MnO4 minus permanganate is reacting with the oxalate C2O4 2 minus. Now the reaction is taking place in acidic medium. MnO4 2 minus, it will be reduced to Mn2 plus. Next, oxalate will be oxidized to CO2. Next, without the need of balancing the reaction, how to proceed to simplify the numericals? Say, since the reaction is taking place in acidic medium, we know the valency factor of the MnO4 is 5. So, valence factor of MnO4 is 5. Next, the oxalate, valence factor of oxalate is always 2. Valence factor of C2O4 2 minus is always 2. So, if you remember the valence factor of a certain well-known species, we can easily proceed to simplify the numericals. Next, in every redox reaction, the equivalence of first reactant is always equal to equivalence of second reactant. Therefore, equivalence of MnO4 minus is equal to equivalence of oxalate. Equivalence, for equivalence we can use any suitable formula. For example, equivalence means weight by gram equivalent weight, or normality into volume, or moles into valency factor. Any one of these suitable formulas can be used to calculate the equivalence. For example, if the reaction takes place in the solution medium, equivalence of the KMnO4 is equal to equivalence of the oxalate. Here this is normality, this is volume. This normality and volume. So in the numericals, if they give the molarity, you try to convert that molarity into normality by using this relation. Normality is equal to molarity into valency factor. See, if you remember the valency factor, and if molarity of the reacting species are given, by using valency factor and molarity, we can easily convert into normality. Then from normality, we can use this relation. Equivalence of the first reactant is equal to equivalence of second reactant. So by using this formula, if they give the normality and volume of first reactant, if they give the normality, we can calculate the volume like that. So based on the equivalence principle, all redox reactions can be easily simplified.